Good morning, math humans. We're going to do 4.4b today. We're going to be talking about the second fundamental theorem of calculus. Our objectives are that we're going to use and understand the second fundamental theorem of calculus. Then we're going to find the net change in position, which means either total distance or displacement. All right, the first fundamental theorem of calculus is what we've talked about yesterday. Remember, capital F means I'm talking about an integral, and it just basically says I can integrate, I can find the area under a curve, I can do a variety of different things. The second fundamental theorem of calculus is amazingly entertaining, and if you'll notice what it says, I'm going to take the derivative of an integral. Notice that my top index is a variable, right? The bottom index can be anything it wants. And then notice that I have my top index is one variable. The inside portion of my integral is a different variable. But when I take the derivative of the integral, I actually get the integral inside done with the top index. And then typically then I would take the derivative of the top index. In this case, the derivative of the top index is 1. All right, so the notation is really important, and you're going to use the second fundamental theorem of calculus when I'm taking the derivative of an integral, right? And another key thing that you want to look for is that the top index is a variable. The chain rule is going to kick in, so once I substitute this into here, then I have to take the derivative of the top index. So let's just do an example. So I want to find the derivative of f of x is equal to pi over 2 x cubed cosine of t dt. And I'm actually going to do this problem two different ways so that I can illustrate the fundamental theorem of calculus. So the first thing that I'm going to do, I'm going to put method 1. And when I start, I'm actually going to do the integration. The integral of cosine would be the sine of t evaluated from pi over 2 to x cubed, okay? So then that's going to be the sine of x cubed minus the sine of pi over 2. Remember, pi over 2 is up here, and so it's going to be a 1. So this would be the sine of x cubed minus 1, okay? So that would be if I had taken, if I had done this by hand, sorry, that's my integral, but then I have to take the derivative. So now I'm going to do the derivative of this, and when I get the derivative, this is the chain rule, the derivative of sine is a cosine. What starts inside stays inside. The derivative of a negative 1 is 0 times the derivative of the inside, 3x squared, okay? So then if I did f prime of x, that would equal the cosine, sorry, you can't see that, of x cubed, and then I would put my 3x squared out front. So method number 2. The reason that this is glorious, I'm going to put a big old star by it, because this should be the way that you manage the equations. I can get here, but oftentimes when you're asked to take the derivative of an integral, the integrals are hairy. And so if you remember the second fundamental theorem of calculus, you don't have to work very hard. So if I take the derivative of this integral, it says that it's going to be the function evaluated at the top index times the derivative of the top index. F prime of x is 3x squared cosine x cubed. Hallelujah, all done. The kicker is you have to remember, it doesn't matter what the bottom index is, because if you'll notice, it ended up going away anyway. The second fundamental theorem of calculus says if you're taking the derivative of an integral, I'm going to substitute the top index into the function. and then I'm going to multiply by the derivative of the top index, and that would be the chain rule, and that's it. So let's do another example, and we'll show you how it works, okay? All right, actually, I lied. Let's talk about net change first. Okay, net change says if I have an integral from a to b, f of x dx, it's just going to be f of b minus f of a. It's very similar to the mean value theorem for integrals. So we call this the net change, but what we're going to start talking about is displacement versus total distance traveled. Okay. So let's do an example, or I guess it's not really an example, but an illustration. And then we'll continue this discussion in a minute. This says the velocity of a particle moving along a straight line where s of t is equal to position at time t. So the way that we're going to talk about this right now is if s of t is position and s prime of t is velocity, and then I could take the integral of s prime of t dt, I would take the integral of velocity, that would give me position. Okay, another way to think about this as part of the net change is that the integral from a to b of v of t dt is just going to be s of b minus s of a. Okay, so sometimes I may or may not have the integral, and so it's kind of like the mean value theorem, but I can find the position function and just evaluate it at the endpoints, the difference of the endpoints, and then this would give me displacement or net effect. Okay, so the next thing I want to talk about is displacement versus total distance. And we're going to talk about it from a graph. Okay, so here's my handy dandy graph, and let's say I have a function, and let's say this is A and this is B. This is a positive area. It'd be nice if you could see it, wouldn't it? This is a positive area, this is a negative area, and this is a positive area. Okay, so if I tell you that F is going to be velocity, so if I integrate v of t dt, I'm going to get position, or s of t. If I have a positive area, then I am moving to the right. Right? Positive means I'm going to the right. If I have a negative area, that means I am moving to the left. So when I do an integral of velocity for position, and I do s of b, I'll move my thing in just a second, minus s of a, then that means this is the net effect. So that means that I went to the right a little bit, I went to the left a little bit, and then I went back to the right a little bit. So the net effect is called displacement. Okay? So now we're going to talk about this same situation, and if I took the integral and I did the absolute value of velocity, dt, that means now that all of the areas are positive, which means that if you think about it, I went to the right, I went to the right, I went to the right, so this is total distance. Okay, so the difference between the integral of v of t dt, I'm going to go right, oops, I forgot the arrow, left, right, and so this is displacement. This is the net effect. Where do you end up after you walk right, left, right? Versus, if I take the absolute value, that means that I'm always going to the right, which means that that becomes my total distance. All right, let's do a second example. And we're going to have a particle is moving along a line so that its velocity is v of t is equal to t cubed minus 10t squared plus 29t minus 20. And I'm going to have several tasks. The first of those tasks is what is displacement, I guess there's a v in there, of the particle from 1 is less than or equal to t is less than or equal to 5. The second task is what is the total distance traveled over the same time interval. 1 is less than or equal to t is less than or equal to 5. Alrighty, so for A, for displacement, displacement is the net effect. So displacement is equal to the net effect, and that just means it's going to be the integral from 1 to 5 of v of t dt. Okay? And for purposes of discussion, in theory, you could put this in your calculator and get a value, because doing the integration is not the focus. It's just talking about what does that integral represent. If I did that math, I would get 32 over 3 feet. And so then I would write that my displacement, as I report my answer, is equal to 32 over 3 feet during the time interval from 1 to 5. Now, when you are reporting an answer, it's very important, just like when we're talking about the derivative at a specific point in time, we're also talking about an integral over a specific time period. So you have to make sure that when you're reporting that you tell over what time period that particular situation happened. All right? The B part wants to talk about total distance. All right? And remember that total distance is going to be the absolute value of the function, because then that means that all of the areas are positive. And again, you could just put this into your handy-dandy grapher. So if I were to put this in my calculator, I would have one absolute value, and then I would do t cubed minus 10t squared plus 29t minus 20. I would do the absolute value. Let me show you what I think is a more efficient way to do it. So I'm going to go to my grapher, and I'm going to enter x to the third, and then I have minus 10t squared plus 29t minus 20, and then I'm going to quit. I'm going to do math 9, and I'm going to integrate from 1 to 5, and then inside I'm going to do math number absolute value alpha f4 y1, because that's the function that I entered. I'm going to put a dx, and when I do that math, and then if you wanted it in fraction form, you could math frac it, but you would get 71 over 6, and so then my total distance is going to equal 71 over 6 feet during the time interval from 1 to 5. Alrighty. If you have access to a calculator, I think it's a good idea to put the equation into your y equals, because then if I use that equation multiple times, I'm going to have less likelihood of making mistakes. If you had to do this by hand, really bad math, then I would make sure that I'm showing all of my work to do that by hand. All right, that's it for today. That is our discussion on displacement and total distance. Hope you guys have a good day. I'll see you soon.